Great, good. So what I'm going to be talking about is decarbonization beyond the electric sector. So I'll basically be picking up where the other Eric left off. And I'll be focusing in particular, not so much on the kind of nuclear core, but on applications and business models. So, you know, stepping back for a moment, we have a decarbonization challenge, and many, you know, the current policies scenarios show that we will fail to decarbonize adequately by 2040 and probably by 2050 as well. So we need to do a lot more than what we're doing right now. And you know, you can think of it like this. We've all seen this graph here, and I've sort of put some, you could think of it as like a to-do list that I've put on top of the graph. We see this graph, but this graph is not going to happen like this by itself. So what needs to happen is, for example, repowering all the coal plants in the world with a new heat source, converting all liquid fuel use to carbon neutral fuels, replacing natural gas use with ammonia or hydrogen, while developing significant generating capacity in Africa and electrifying all the applications that we possibly can. And actually, we only have 30 years to do this. So we are really far from even having a plan to accomplish this kind of transformation. So we recently published a study called the Missing Link, How Hydrogen-Enabled Synfuels Can Help Us Achieve the Paris Goals. And I'm going to take you through some of the concepts that we explored in there, which really have to do with how can we apply small modular reactors, or as we like to call them, advanced heat sources, to helping with these challenges. So first of all, we like this idea of the impossible burger. And the impossible burger is something that is made out of vegetable matter, but it tastes like a burger. You can eat it like a burger. You can buy it where you buy burgers, and but it doesn't have the impacts of the meat value chain. This is kind of a drop-in substitute for a burger. And what I want to explore in this presentation is the large-scale production of drop-in substitutes for liquid fuels. So we currently use, maybe this year we're using a little bit less, but the projections are that we will bounce back quite quickly to using around 100 million barrels of fossil fuel per day. That's a very large amount of energy. And if we want to produce this if we want to produce drop-in substitutes through the production of hydrogen and then making either ammonia or synthetic hydrocarbons, the fundamental cost that we face is the cost of that hydrogen. So, for example, in ammonia, about 85% of the cost of finished ammonia really relates to the cost of the hydrogen that you use to make the ammonia. In fuels, it's a little, in synthetic hydrocarbons, it's a little bit different because you have to also get some carbon in there. But largely, it's the energy input cost, which is determining the cost of the finished synthetic product. And we like to call this graph the guardrails of the hydrogen economy. If you want to use direct use hydrogen in a car or something, you know, it can be a little bit more expensive than what we're talking about here. But if you want to use it to make cost competitive, impossible burgers in the fuels area, if you want to make cost competitive drop-in fuels, you need to be able to produce hydrogen for somewhere between 50 cents and $1.50 a kilogram. That's very low cost. If you're above that, you're producing fuels which have a sort of market price above the kind of the experience of the market with oil prices and finished petroleum products. Does that make sense? So if we're above those costs, our finished synthetic fuels will cost a lot more than the historical prices that we're used to in the liquid energy sector. So how do we make hydrogen and synthetic fuels at these highly competitive costs? This is where we start talking about deployment models and business models. So the first, there's really, if you want to make nuclear energy extremely cheap, which is what we need to do, you really have to either bring the factory to your project. So Eric was talking about serial production and all of that. The problem is if you don't have a place where you can, if you don't have a customer that's going to buy the output from your factory, it's hard to justify the kind of investments that make that factory efficient and cheap. If you're Tesla and you can get 300,000 orders for your car before you even build your factory, then you can build a big factory and lower the costs to the point where you have a very cost competitive product. So we need to be thinking like this. It turns out that liquid fuels markets and hydrogen markets to make liquid fuels enable the kind of large scale projects and large scale demand for these advanced SMRs. So what we see here is a 36 SMR hydrogen gigafactory. And we have on the top there, we have the factory that's making the reactor components and the mechanical systems, highly automated. And then the left at the top, we have a flatter building, which is making the precast concrete components, which are then all being assembled as part of that production process into the reactor farm that you see in the middle of the screen. And that is providing heat and electricity to the hydrogen production and synthetic fuels production systems that you see in the lower right. So this is ultra low cost nuclear energy dedicated for hydrogen and fuels. This is bringing the factory to the project. The other model is to bring the project to the factory. And in this case, the factory is a shipyard, an advanced modern shipyard, where there's highly automated processes like welding and panel production, and where large modules, as you see in the foreground, are produced repeatedly by the same teams in highly productive work arrangements. And then those are brought together, those are more or less finished and then brought together and connected into the whole to make the whole ship. And in this case, what we're making in this visualization here is a floating production platform, which makes which has advanced heat sources on board and makes hydrogen and synthetic fuel, storing the fuel in the hull and offloading to, in this case, a bunker ship, which is going to be refueling ships. So this is a visualization of making synthetic fuel for the shipping industry. The large green ship is not a moving ship. It doesn't have a propulsion system. It's anchored in one place where you want to produce the fuel. And we think this type of ship, we just completed a very detailed techno-economic study of these approaches with the Electric Power Research Institute, which will be published shortly. And we think this can produce ammonia for an equivalent oil price of about $60 a barrel. So $60 a barrel of finished product made as ammonia. So very cost competitive with the long-term cost of finished oil products. So I'm not gonna, the slides will be available. I'm not gonna go through this in detail, but our report shows how the cost of hydrogen is strongly related to capacity factor and the cost of the energy that you're providing. But having low cost energy and a low capacity factor is not sufficient to make low cost hydrogen. And so you can see that, for example, a second of a kind, which is like the proposed Sizewell C project by EDF in the UK, which everyone thinks, oh, you know, they're lowering the cost from Hinkley, but it could still be quite expensive. That is more or less competitive making hydrogen with the most cost-effective large offshore wind project in the UK. So we put them both in our cost of hydrogen analysis tool, and you know, they come to a very similar cost. And that's the difference between that's capacity factor, and it's also the effect of being able to use heat in the production process as well as electricity. So what you do see there over on the right is that if you have low cost nuclear plants, such as might be possible producing the plants in a shipyard, you can achieve very low cost hydrogen that meets the requirements that I laid out in that guardrail slide. So very briefly, we do a scenario in our report that basically says, what if we have to replace all of the liquid fuels that we currently use on planet Earth? And we show how you can accomplish that substitution. And in fact, using these shipyard manufactured plants, we show that the total investment required to achieve that conversion is less than the total investment of just continuing to produce the oil that we need between now and 2050. So in other words, the oil industry is projected to spend around $24 trillion between now and 2050. And just to maintain that flow of oil, if you did this strategy, you would spend 17 trillion. So it seems like it might be cheaper to save the planet than to destroy it. And by the way, if you were using renewable energy systems like wind and solar, and in this case, I modeled combined wind and solar projects using 2040 NREL projected costs for this, you would need to invest $70 trillion to produce the same amount of fuel. So this just basically looks at how many shipyards would you need to have and how many production platforms would you need to have. You'd need to have a lot of production platforms, but this is you know, there are 60,000 large ships operating in the world, so we only need 14,000 of these platforms. This is, as I said earlier, this is a very similar scale to the current oil and gas industry. So it looks like a lot, but that's because it's a big industry. And then, you know, this is roughly how many shipyards you would need and so forth. And there are well over 200 large-scale shipyards operating today. So the kind of question for Sweden is, where do we get the biocarbon for large-scale synthetic drop-in hydrocarbons? Well, stop burning it. Today, the paper industry and proposed biorefineries in Scandinavia all assume that you're going to get your heat from continuing to combust waste biomass. And you know, as these plants get more efficient, they actually end up with excess biomass. And many of the proposals are assuming that you burn that extra biomass and make electricity. So one way to produce a large, so let's stop burning this and convert the excess biomass to liquid fuel. There's a work going on in the US looking at MIT has a project looking at this, looking at nuclear plus biomass to make synthetic drop-in hydrocarbons. Nuclear-enabled biomass gasification increases the carbon efficiency by getting the heat and hydrogen required from a nuclear source. So instead of burning 2/3 of your biomass to make the heat and putting that carbon in the air, you can actually make 100% of your carbon into the fuel. So this can produce, depending on the cycle used, can produce up to 3 times the fuel compared with traditional biomass to liquids. This enables large new markets which are outside the currently less profitable paper sector. It also combines 2 industrial sectors where Sweden is very strong: nuclear and biofuels processing. And it addresses a critical global need for the decarbonization challenge. So, given the scale and urgency of the required clean transition and the ongoing growth of the global energy system, we really need to look at how to leverage all zero carbon hydrogen production options. And advanced heat sources, whether they're light water sort of advanced SMRs or higher temperature production, higher temperature reactors beyond that, are able to power the production of very large scale, low cost hydrogen, which can then be used to make synthetic fuels. But we really need to look at the deployment models and how to get the costs down, how to get down that cost curve. We can't just take our current designs and say we're going to make them smaller. It really has to be a transformation of the production and delivery system for the heat sources. And our report, The Missing Link to a Livable Climate, really sets out a kind of a pathway to achieving this kind of decarbonization. And really, these are sectors right now for which there's no credible solution being proposed. So thanks very much. That's my presentation. I'm happy to take any questions.
Truly fascinating presentation. So starting just with that interesting number that you proposed there, that the cost of hydrogen needs to be somewhere between 50 cents and $1.50. Do you have also, what does that mean in terms of dollar per kilowatt hour in terms of levelized cost of electricity? Have you made sort of an estimate of that?
Yeah, sure. So there's actually some very good reports on this. So a depreciated light water reactor, such as the kinds that you have in Sweden today, which has not, if you assume it has not had significant capital investments recently. So it's more or less you're dealing with the operating costs of the plant. At least in the US market, those can produce hydrogen for around, or projected to produce hydrogen for somewhere between $1 and $1.50. And that's assuming high temperature electrolysis systems. So in other words,
so what I mean is that I guess you need electricity at some price to get to that.
Yeah. So that cost is somewhere between $25 and $30 a megawatt hour.